Hello to everyone. We are talking about paper titled Adaptive Block Coordinate Descent for Distortion Optimization, presented by Naitsat Alexander from Technion. In this paper, we are dealing with geometric optimization problems in which we optimize distortion on meshes to obtain a high-quality mapping of geometric data. Distortion minimizers are inversion-free mappings that induce low shape distortions on meshes, and those mappings are desirable in many geometric processing tasks. Let's see some basic example of how a planar shape is deformed during distortion optimization process on a triangle mesh. And another example of distortion optimization on a tetrahedral mesh. A distortion optimization problem has a long history in geometry processing. Solving it is essential in many related applications, including such classical tasks as point-to-point shape deformations, surface parameterizations, which is widely employed in computer graphics for such tasks as a texture mapping. Also, in recent methods, distortion optimization techniques are used for shape matching applications between surfaces. And there is many applications of three-dimensional distortion optimization for computing volumetric mappings, for example, in physical simulations of elastic materials, and etc. And this is only a part of applications. Obviously, computing inversion-free maps is behind many other methods of geometry processing. Now let's consider a general formulation of the problem. In general, we are solving a problem of minimizing geometric energy E that measures how much a map F deviates from a given class of deformations. For example, from a class of rigid transformation. F is a piecewise affine mapping, so it can be expressed by target vertex coordinates x, and this leads to the optimization problem over vectors of target coordinates in 2D or 3D. Energy E is defined in a finite element manner. That is, on triangle meshes, it's a weighted sum of distortions of triangles. Similarly, on tetrahedral mesh, it's a weighted sum of tetrahedral distortion. That is, the energy E is a total distortion that F components induce by mapping source elements to target elements. And our task is to obtain as low as possible sum of distortions of those elements and to prevent flips. That is, we want to keep the given order of vertices. Now we give a formal definition of this constraint optimization problem. The energy E is defined as a volume-weighted sum of distortion D of linear components of the map that are the map's Jacobians, defined on simplices. And here D is a geometric measure that estimates a local shape distortion defined per simplex. We compute a target vertex positions x that induce minimal energy E under the following constraints. The first one is the inversion-free constraint expressed by the determinant sign, and the second one is a given constraints on a target vertex position. Now let's define a measure D of the local distortion. So we assume that D is a rotation invariant measure that estimates a local deformation of Euclidean lengths induced by linear components of F. Those measures can be expressed as a function of signed singular values of Jacobians. So if this is a signed singular value decomposition, then we assume without loss of generality that only the first singular value can be negative. And then according to this assumption, D is a function of the singular values, and the sign of the determinant equals to the sign of the first singular value, sigma 1. Therefore, if is inversion-free if and only if sigma 1 is positive. Here is a short overview of most common distortion optimization methods. Most methods are iterative solvers that start with some inversion-free initialization and modify target coordinates along energy descent direction D, computed via the following sparse linear system, where H is a Hessian of a quadratic proxy of energy E. There are many methods for constructing H. Those methods are typically divided into first-order solvers, in which H is a function of first-order energy derivatives, and into second-order solvers, in which H is a function of both the first and second-order partial derivatives of E, computed with respect to x. At the end of each iteration, line search methods are used to find a sufficiently good reduce in energy E along the obtained search direction D. Note that vast majority of first and second order solvers have to be started with inversion-free initializations. that are possible to compute only in certain scenarios. For example, in parameterization, disk topology surfaces can be mapped into disk by TAT embedding and its variants. Although the distortion in TAT embedding can be huge, it has theoretical guarantees to be inversion-free mapping onto convex planar domains. Starting with inversion-free initial map, distortion solvers are designed both to minimize distortion and to prevent orientation flips. And there are many methods for keeping the initial orientation of simplicial map during optimization, such as a design of distortion measures with special barrier properties. We'll discuss it in next slides. Other methods for keeping positive orientation is the line search filtering, and there is also methods for keeping global bijectivity, which we'll discuss at the end of the presentation. Despite having theoretical guarantees, practically that embedding has certain implementation-related limitations. With floating point arithmetics and on challenging meshes, it can fail to produce inversion-free maps even if the target domain is convex. Another common case in which it's not easy to compute inversion-free initialization is a constrained parameterization with anchor points fixed in the plane by given hard positional constraints. And of course, it's much more challenging to compute inversion-free initializations for volumetric problems. So, in view of those limitations, a number of methods were proposed for repairing an invalid initializations that contain inverted and collapsed elements. To explain briefly those methods, consider a basic deformation of a triangle grid with one flipped triangle marked in yellow. Methods for repairing invalid maps can be divided qualitatively into vertex-based methods that modify vertex position in order to fix inversions, and a simplex-based method that first treats separately each simplex, for example by cutting mesh into disconnected simplices. Then invalid simplices are fixed separately and their vertices are stitched together by carefully designed matching constraints. Distortion optimization methods and methods for repairing invalid maps have been extensively studied by the computer graphics community, but due to the inherent differences, in most cases, the treatment remains separate. Nevertheless, both aspects of the problem play a crucial role in finding a good solution to a given geometric optimization problem. Therefore, we propose a method called adaptive block cardinal descent ABCD, aimed at solving in a single algorithm both the problem of fast distortion optimization and the problem of fixing invalid elements. Our algorithm is a vertex-based method that can be integrated with any first or second order solver. It is based on the two major ideas. The first idea is an alternating optimization of newly proposed distortions that penalize invalid elements and of standard distortions modified in such a way that we both can fix existing invalid elements and prevent generation of new ones. The second idea is an adaptive partitioning of vertices into coordinate blocks according to the geometric configuration of the problem. So let's start with the first contribution of our method and explain how distortions are modified in ABCD. First, let's review the most common distortion measures employed in geometric optimization. Those are isometric and conformal distortions, which are lengthwise and angle-wise measures respectively. Usually, if you collapse target elements, then those measures approach infinity because of barrier terms that explode on degenerate elements. For example, consider the following symmetric Dirichlet energy that measures isometric distortions. The barrier term of this energy prevents positively oriented elements from being collapsed. And this is a good property, but under invalid initialization, this property of the energy also prevents optimization from fixing the existing conversions. And that is a bad property. Therefore, we aim to modify existing energy in such a way that both tasks of fixing invalid simplices, that is inverted or collapsed elements, and preventing generation of new ones is possible within the same procedure. We modify distortion energy according to geometric configuration of the mapping obtained in the previous iteration. So we denote by SC the orientation of the simplex C at the previous iteration I, and assume the following deformation at iteration I plus 1. We use the previous orientation of simplices to modify the original measure D as follows. On valid simplices, d equals the original measure plus the borrowed term in order to prevent new foldovers. And we filter out contributions of simplices that were previously inverted or collapsed. We denote by d tilde distortion d modified according to those rules. With this modified distortion d tilde, invalid elements are no more blocked and thus they can be fixed during the energy optimization. Moreover, after they are fixed, optimization will prevent appearance of new inversions and collapsed elements. This approach enables an efficient alternating optimization of classical rotation invariant energies and of the measures designed for repairing invalid simplices without badly interfering with each other. Next, we define the second class of the measures that penalize invalid elements. Assuming the positive orientation of the source elements, a simplex is inverted under F if it has a negative volume proportional to the product of its signed singular values. We penalize both the number of inverted elements and the negative product of their signed singular values. Here, lambda is the uniform cost of a single invalid element. Negative gradients of d flip move vertices of inverted simplices toward flipping them from negative to positive orientation. Since orientation of a zero volume simplex is not well defined, we consider collapsed simplices as a separate class of illegally deformed elements that are penalized by the following measure. Negative gradients of this measure move vertices of nearly collapsed elements toward unfolding those elements to a position with non-zero volume. To simplify the task of repairing invalid elements, we combine those two measures into a single penalty of invalid elements. This measure penalizes both the inverted and collapsed elements. And clearly, this measure is SVD-based energy, and thus it can be minimized along with the usual rotation invariant distortions in an alternating optimization pipeline. So we start with a fixer stage in which we optimize invalid penalty F to repair inversions and collapsed elements. After a certain number of iterations, we switch to minimization of the modified rotation invariant distortion d tilde. When all invalid elements are fixed, further processing is devoted solely to d tilde, which at that stage is equal to the original energy d, and the process is terminated after convergence of all measures. Here, dashed lines depict the interval of line search that we have modified for our needs. Please see the paper for details on our enhanced line search and on ABCD convergence criteria. Now let's talk about adaptive vertex partitioning. The vast majority of existing geometric solvers are global methods. Those methods update the entire set of target coordinates simultaneously. Most recent solvers are global methods, and among the few purely local methods are block coordinate descent BCD strategies with small constant blocks. BCD methods are easily parallelizable, but unlike in global methods, in BCD it may take more time for geometric information to propagate from one part of the shape to another. Our algorithm is a hybrid method based on adaptive block partitioning strategy that solves distortion minimization problem separately over blocks of target vertices of varying sizes. Starting with the invalid non-injective initial map, ABCD behaves as a modified block coordinate descent up to the point where the current mapping is cleared of invalid simplices. Then our algorithm converges rapidly into the chosen global solver. To understand our adaptive partitioning strategy, consider the following deformation of a planar bar into a spiral, with inverted triangles colored in yellow and areas of high isometric distortion d tilde are colored in red. If d tilde is minimized, then vertices sharing only inverted triangles are static vertices, fixed in place because they have zero descent direction, while vertices of positively oriented elements are free to be moved at the current iterations, and geometric information from free vertices cannot propagate through static vertices. To illustrate it, consider a slight movement of the free vertex and observe how it impacts trajectory of other free vertices. So geometric information from these vertices propagate and fill all the vertices that can impact each other. That same process applied for remaining free vertices yields a natural selection of other vertex blocks. By the construction, the obtained blocks can be modified separately in the current iteration without interfering each other. Formally, we define a set of free edges that share free vertices and build the connectivity graph G of those edges and vertices. Then the coordinate blocks are the connected components of graph G, and in this case, free vertices are partitioned into 3 blocks. We get the opposite configuration when minimizing invalid penalty F. Here, static vertices share only positively oriented elements, and vertices of inverted triangles are free to be moved. We use edges between those vertices to find 3 connected components. Each of those blocks is a flipped segment of the spiral. Anchor points are by definition static vertices. Therefore, anchor points can increase the number of blocks. For example, in this inversion-free spiral deformation, anchors, depicted by blue points, divide vertices into 6 blocks. In the paper, we prove that a single optimization iteration with our adaptive partitioning method results in a distortion energy that is lower or equal to the energy attained by a global solver iteration. Another advantage of our algorithm is that by using graph coloring, we can optimize different blocks in parallel. Now we are in a position to present the full ABCD algorithm. First, we compute a global descent direction with respect to a given distortion measure. Then we use our adaptive partitioning for obtaining vertex coordinate blocks. Those blocks are optimized in parallel by using in each block a chosen solver and line search method. We start with the invalid element penalty and alternate between this measure and a modified rotation invariant measure d tilde, such as a conformal or isometric distortion. Our algorithm is very general and is compatible with most first and second order solvers. In the following examples, we'll use gradient descent and projective Newton solvers for minimizing f and d tilde distortions respectively. In the paper, we explain why we chose those geometric solvers. Also, note that unless stated otherwise, we assume that d is a symmetric Dirichlet energy. Alternating optimization and adaptive block coordinate descent strategies are aimed at robust geometric optimization. ABCD can recover fast from highly distorted invalid initializations that contain thousands of collapsed inverted elements and converge fast to low distortion mapping under hard positional constraints, like in this example of randomly initialized problem of a planar shape deformation. Other applications of ABCD include constrained parameterization problems. In this example, we compute TAT embedding and then move 8 target endpoints on octopus legs into their prescribed position in the plane. Like in this case, such initializations almost always result in collapsed and flipped simplices, and therefore such problems with hard positional constraints cannot be handled by most geometric solvers. However, those constrained parameterization problems can be solved fast by ABCD. Another example of constrained parameterization with ABCD. Here we place endpoints of a space-fitting curve along the corners of texture image. And by running ABCD, we are able to align precisely the texture image on the curve. Using ABCD for unconstrained surface parameterization initialized by TAT embedding is more reliable than using standard solvers because ABCD can repair invalid triangles that can be caused by certain numerical issues. In this example of a Hilbert curve with uneven triangulation, our algorithm fixes initial inversions and computes isometric parameterization. In standard initialization schemes, producing initial map free of holdovers often costs many more additional iterations for parameterization algorithm because often the initial convex shape is very far from the final shape of the UV map. It therefore seems that mapping to other domains that match the structure of a source mesh should be a much better starting point if the algorithm can fix occasional inversions. Our algorithm can fix those inversions, and therefore it can begin with a better starting point for accelerating surface parameterizations. Here, to obtain a better initialization, we parameterize a decimated mesh. Then we use a planar deformation induced by the decimated UV map to construct an initial map in the higher resolution. As you can see, this initialization is much more close to the expected shape of an optimized UV map. Our algorithm can repair effectively inversions presented in this initial map, and then it converges fast to the final isometric parameterization. Here is an example in which it takes only a few ABCD iterations to fix inversion and then only a few iterations of ABCD isometric optimization to converge, while standard approach requires much more costly projective Newton iterations. We propose another method for accelerating isometric parameterizations by initializing ABCD with fast conformal mappings. There are many algorithms of fast conformal flattening based on linear methods. It takes nearly the same time to compute that embedding or to compute those fast mappings. But conformal maps, such as boundary first flattening, BFF, result in the shape that is much closer to the final isometric parameterization. A BFF can produce a small amount of invalid triangles, and therefore initializing ABCD with BFF can be much faster than a standard approach. And here is a comparison of our parameterization method with a standard one. We tested our approach on the progressive parameterization dataset. In particular, we selected meshes on which BFF fails to construct inversion-free map and compared our conformal linearization approach with a standard isometric parameterization. Here is a summary of our results, illustrated as a histogram of runtime ratios between the two methods. In the vast majority of cases, depicted by blue beans, ABCD with BFF initialization runs faster than projective Newton with stat embedding. Note that running our parameterization method is also much more reliable, because on many collected meshes, stat has a floating point precision issues, and it fails to produce inversion-free maps. On those meshes, projective Newton does not converge at all, and therefore we did not include those results into the histogram. But obviously, with those results included, our algorithm will look even better. And our algorithm works also in 3D, where it can recover from highly distorted initializations with many invalid tetrahedrons. We show some results of computing volumetric maps with ABCD. Here is the source mesh with anchor points marked in blue. Initialized with flips, we use two isometric energies in ABCD that we modify according to our algorithm. The first one is the symmetric Dirichlet energy and the RAP energy, which is another popular distortion measure. Those are the results. More examples with constrained volumetric mappings. Here is a comparison of our algorithm with the large-scale bounded distortion method LBD in 3D. We tested different parameters for LBD. In most cases, it did not fix all the inversions, and it is only capable of bounding conformal distortion, while our method can minimize directly many different distortions. We also compared our algorithm with combinations of different existing methods for optimizing distortions and repairing inversions, both in 3D and in 2D. Details of comparing those methods with ABCD appear in the paper. To summarize, we have demonstrated over a variety of geometric problems that ABCD exhibits superior robustness compared to existing method in terms of number of invalid simplices at the distortion level, and it is able to deal with more complex positional constraints. Finally, let's discuss algorithm limitations and how to resolve those limitations. Since we are using hard positional constraints, we cannot move badly placed anchors. For example, in inversion-free parameterization, boundary curves of rest and target meshes need to be oriented consistently. Inconsistent placing of boundary anchors can result in unrealizable results, as shown in the following example, where ABCD managed to compute inversion-free map, but the mapping is non-locally injective, and it leads to texture artifacts. Of course, if all anchor points are placed inconsistently, then it is impossible to compute positive-oriented map at all. This example shows another common limitation of inversion-free mapping algorithms. Inversion-free maps are not always bijective. However, it is possible to impose additional constraints to prevent boundary overlaps and to guarantee that the inversion-free maps will be globally bijective. And there is several studies on how to impose those constraints, Those methods can be integrated with ABCD. Here is a toy model example of combining the method of scaffold meshes with our algorithm for obtaining a globally injective map. Our algorithm has more contribution, but unfortunately there is not enough time to present it all. So please see the paper for additional contribution. The first one is a more advanced method of vertex partitioning that gives a better trade-off between the number of blocks and the block sizes. It is called local global blending, and in many cases it improves results on middle resolution meshes. Another contribution is improved elimination criteria. And of course, it is important to know when geometric optimization should be stopped in order to get good results without introducing redundant iteration. For details, please read the paper, and for implementation, please see the GitHub page. Thank you for listening.